Are here to lecture you on the change of entropy in the system and surrounding according to the phase transition.
So to give you a brief overview of entropy, entropy is a state function and can be thought of as a measure of disorder in a system. Molecules in the gas phase have the least order of all the phases because they can move about freely and take up the volume of their container. Gases therefore have the greatest entropy. Solids have the lowest entropy as the molecules are arranged in a pack ordered form. So for entropy, gas is greater than liquid, which is greater than solid. So as you can see, there's more order in the solid than the gas phase, so gas has more entropy. Now we will address our prompt by connecting changes in entropy with phase changes. We would like to preface our lecture by mentioning that entropy is not path dependent, so it doesn't matter how a system goes through its phase change. When phase changes, we would expect that a phase change would be accompanied by a change in entropy. For example, when a liquid boils, a compact condensed phase is converted into a widely dispersed vapor phase. Clearly, the molecular disorder in a gas will be greater than that in a liquid, so there is an entropy increase upon vaporization.
Laura has given you a general detail on how entropy changes based on phase transition. We'll go into more of a quantitative work by including what happens when enthalpy is involved. So before we start, we will need to consider a system and its surrounding at a normal transition temperature in order to do all this, and I'll give you a detail on what that means. So TTRS, that's the normal transition temperature for a given phase change. And in this case, for our case, we will say that our normal transition state is 273 Kelvin, which is 0 degrees Celsius, and 1 atmospheric pressure for liquid and ice in liquid water and ice in equilibrium. At this transition temperature, any transfer of heat between the system and the surrounding is reversible, which means that those two phases in the system and the surrounding are in equilibrium. So now moving on to enthalpy. At constant pressure, Q equals delta H at our normal transition temperature, which is defined as the enthalpy change accompanying the transition. And in this case, the molar entropy change of the transition is given by delta S TRS equals H TRS H over T. And now we'll go into details on how this plays out with both types of reactions. So now you have exothermic and endothermic reaction. If the phase transition is exothermic, which means that delta H, normal transition temperature, is 0, by freezing or condensing, the entropy change is negative because we defined that entropy change is delta H over T. If this is negative, this will be negative. So what this means is that the transition reflects a greater ordering of the phase that is formed during the transition. For example, if solid is formed from a liquid during the freezing phase, the negative entropy change confirms that the solid is more ordered than the liquid. And in opposition, the endothermic, which is delta H is bigger than 0 and delta S is bigger than 0. And this means that the entropy change is positive, reflecting the higher degree of disorder in the phase that is formed during the transition.
Alright, so moving off of what Jay said, with the exothermic and endothermic processes, the changes in entropy during a phase change are either called delta S vaporization or delta S fusion, where delta S vaporization is going from a liquid to a gas, and delta S fusion is going from a solid to a liquid. These equations are denoted by delta S vape is equal to the enthalpy of vaporization of our substance over the temperature of vaporization. And similarly, we have delta S of fusion, which is equal to the delta enthalpy of fusion over the temperature of fusion for that substance. Keeping this in mind, the delta S total for every system, be it fusion or vaporization, is going to be equal to that delta S of the system plus the delta S of the surroundings. So, given this equation, we're able to see that if the total entropy, this term, is greater than 0, the reaction is spontaneous, meaning that the system is becoming more disordered. On the flip side, if the entropy of the system is negative, the system is becoming more ordered, but is less likely to be spontaneous. So in conclusion, the positive change in entropy is more favorable because this is going to be spontaneous. This is processes such as materials going from a solid to a liquid. Or a liquid going to a gas.